Welcome to Wings of Arrow Advanced Education and Research Organization. To know more, visit our official webpage www.wingsofarrow.in. Find your dream aviation and aerospace jobs at www.wingsofarrow.in/jobs. Now we are going to learn how to find propellant flow rate, total propellant weight and propellant grain burning area of solid propellant rocket. Consider the following requirements are given for making preliminary estimates of performance for solid propellant rocket motor. Sea level thrust is 2000 pound force, average thrust duration is 10 seconds, chamber pressure is 1000 pounds per square inch, ambient temperature is 70 degree Fahrenheit, and propellant is ammonium nitrate hydrocarbon. The properties of this propellant are K is equal to 1.26, capital R is equal to 76.82 foot-pound force per pound meter degree Rankine, T1 is equal to 2790 degree Rankine, R is equal to 0.10 inch per second, and rho suffix B is equal to 0.0546 pound meter per inch cube. A given actual value of C star is equal to 3967 foot per second can be shown to imply a correction factor of zeta suffix C star is equal to 0.997. Assume moreover a thrust coefficient factor correction factor of zeta suffix Cf is equal to 0.98 and optimum operation at sea level. Determine the specific impulse, throat area, propellant flow rate, total propellant weight at sea level, the total impulse, the burning area, and an estimated sea level mass. Assuming that the total impulse to weight ratio is 143 seconds, a moderately efficient design. Given data. Here we consider a solid propellant rocket motor. Thrust at sea level F is equal to 2000 pound force, average thrust duration T is 10 seconds, chamber pressure P1 is equal to 1000 pounds per square inch, ambient temperature T suffix A is 70 degree Fahrenheit, and propellant is ammonium nitrate hydrocarbon. The properties of this propellant are also given. Specific heat ratio is K, gas constant is capital R, chamber temperature is T1, burning rate is small r, and solid propellant density rho suffix B. An actual value of characteristic velocity C star and correction factor of zeta suffix C star, thrust coefficient correction factor of zeta suffix Cf are also given. And also take the nozzle area ratio epsilon is equal to 7.8 and thrust coefficient C suffix F is equal to 1.54. Now we have to find out the specific impulse, throat area, propellant flow rate, total propellant weight at sea level, total impulse, burning area, and an estimated sea level mass. First, find specific impulse. From characteristic velocity, we can write the equation for specific impulse. I suffix S is equal to C star into C suffix F divided by G naught, where C star and thrust coefficient C suffix F are known and G naught is the average sea level acceleration of gravity, which is 9.81 meter per second square. Now substitute those values and solve. We get the required specific impulse is 190 seconds. Next, find throat area of nozzle. Throat area is directly proportional to thrust force and indirectly proportional to the chamber pressure and thrust coefficient. Then write A suffix T is equal to F divided by P1 into C suffix F. Where we know all values, then solve. We get the required throat area is 1.30 inch square. Next, calculate total propellant weight at sea level. The specific impulse represents the thrust per unit propellant weight flow rate. From this, we can solve for propellant weight. W dot is equal to F divided by I suffix S. After solving this equation, we get the required propellant weight at sea level is 10.5 pound-force per second. The effective propellant weight for a duration of 10 seconds is about 105 pound-force, allowing for residual propellant and for inefficiencies in combustion and lower pressure during thrust buildup. The total loaded propellant weight may be assumed 2% larger or 107 pound-force. Now find the total impulse. The total impulse is found from the thrust force. For constant thrust with negligibly short start and stop transients, this reduces to F into T. So multiplying given thrust with thrust duration, we can get the total impulse. So the total impulse is 20,000 pound-force. Next, find the propellant grain burning area. We know the pressure expression in steady burning P1 is equal to K into rho suffix B into R into C star. Here, K is an important new dimensionless motor parameter, which is the ratio of burning area to the nozzle throat area. From this, we can write the expression for burning area A suffix B is equal to A suffix T into P1 divided by rho suffix B into R into C star. Substitute the appropriate known values and simplify. We get the required burning area is 1933 inch square. The factor of 32.2 is needed to convert the units of the density. Now, the loaded gross weight of the rocket motor only can be estimated. Using the value of 143 seconds, we get estimated mass is 140 pound-force. Because the propellant itself accounts for 107 pound-force, the estimate for all the rocket motor hardware parts then becomes 33 pound-force. This includes the igniter, case, nozzle, instruments and insulation. Did you know? Robert Goddard is considered the father of modern rocketry. He built the first liquid-fueled rocket in 1926. The rocket climbed 12 meters in 2.5 seconds. Rockets use oxygen as fuel to power their thrusters. When used with an oxidizer, they created a propellant that moves the rocket around in space. Rockets are used to blast the space shuttle into orbit as well.
If you have further inquiry or requested video, drop down to our mail wingsofarrow@gmail.com. Don't forget to subscribe for more updates. For the time being, take care, stay blessed, inspired and fly high.